So participants, we are very pleased to welcome Dr. Wasim Raja amongst us. Dr. Wasim Raja completed his higher secondary from Cotton College, Guwahati, after which he joined Ramjas College, Delhi University for his graduation. He completed his master's from IIT Delhi. For PhD, he joined Raman Research Institute, Bangalore, where he worked extensively using the techniques of Faraday tomography to study polarized radio sources. After PhD, he spent a considerable amount of time in Cotton College State University, where he was involved in organizing several summer schools in astronomy and astrophysics for college students. After that, he joined Commonwealth Scientific and Industrial Research Organization Australia as a postdoctoral researcher. He was appointed as a research scientist in the same institute in August 2018, where he has been working till date. So I would like to request all the participants to kindly make use of this opportunity and ask as many questions as it is possible to the speaker. So with that, I would like to welcome Wasimda once again. And without much further ado, I hand over the proceedings to you. Over to you, Wasimda.
Hey, thanks, Apurva. Wow, that was that was a thorough research of my past. Thanks for the kind introduction. So, Apurva কোৱাৰ নিচিনা মোৰো এটা ৰিকুৱেষ্ট আছে দেই মোৰ শ্লাইড বেছি নাই গতিকে if you want to help me stop me so that I can fill up this slot. That's a request to all of you. So please stop me anytime you like. Apurva and I think he would be able to coordinate. যদি কোনোবাই কিবা hand raise কৰে মই তোমালোকক দেখা নাপাওঁ দেই মোৰ স্ক্ৰীনত, so please I'm sorry. Apurva, I think will take care of that, right?
Yeah, sure, Da. We are here
Please,
to help
please
you,
feel
Da.
free to stop me.
Yeah,
So
sure.
initially, I had planned to give you a brief overview of what radio astronomy is and what is its future. Where are we at this moment? কি চলি আছে in this field? সেইটোৰ ওপৰত মই এটা টক দিম বুলি ভাবিছিলোঁ। অপূৰ্বই মোক ক'লে যে বৰ্ণালীয়ে last week or in the last session, in the last interaction, Dr. Bernali Das, she from NCRA. Well, she was in NCRA. Now I think she is in CSIRO too. So she gave a talk on radio astronomy. So I'll touch very, very, very briefly upon its history. And I'm planning to keep this talk absolutely devoid of any equations, any technicalities. I hope you'll enjoy the talk. So, all right. So in this talk, I want to briefly introduce what radio astronomy is, what the brief history of radio astronomy is, some key milestones. I have picked, well, there are many, but I have picked up some of my favorites only. So pardon me if I have missed some other key milestones, and I definitely have. So the need for multi-wavelength astronomy, কিয়নো আমি radio wavelength কিয়নো আমার study করার দরকার, just a basic understanding of that need, কিহৰ কাৰণে আমি radio astronomy কৰিব লাগে বা কৰিব দৰকাৰ হৈছে. I'll introduce you to some of the radio observatories around the world. Again, I may have missed, well, not me, I have missed a lot of them, but these days it's easy. You can find them on the internet. So I have picked up some of my favorites. New generation radio telescope. মই যিটো radio telescope ৰ লগত কাম কৰোঁ তাৰ ওপৰত অলপ বেছিকে কম বুলি ভাবিছোঁ because I'm associated with it, but I'll also tell you about a few other new generation radio telescopes that are currently operational. What are the key challenges? Key challenge, key skill set দরকার. I'll be dwelling a little bit deeper into that, and then I'll end introducing you to the square kilometer array, which is a very, very big project, probably as big as humanity has ever seen until this day. And something about that. So let's see where we go. So when did radio astronomy begin? It began with Carl Jansky's what should you say? কি বুলি কয় যে দৃঢ় যিটো এটা ইচ্ছা যে কিবা এটা বস্তু বিচাৰি পোৱা মানে বুজি পোৱা নাই সেইটোৰ ওপৰত লাগি মানে বুজিবলৈ চেষ্টা কৰোতে কি বস্তু তেওঁ I'll give you a very brief মানে what I want to emphasize is his attitude. So this person, Carl Jansky, 1931 চনত, so he was studying interference in radio communication, transatlantic radio communication, telephone দ্বাৰা যেটো আমি সংবাদ কৰো তাত static কিছুমান তেওঁ এই যে disturbance interference এই static কিছুমান তেওঁ মানে ধৰা পৰিছিল। So he was entrusted with the task of finding out what these are, how this can be mitigated, কেনেকে নিবাৰণ কৰিব পাৰি, সেইটো আছিল goal. So he designed an antenna. Well, I think Bell Laboratories designed this antenna, and he was entrusted to find out কৰ পৰানো আহিছে এই সিগনেলটো, যিটো সিগনেলে আমাৰ ৰেডিঅ' কমিউনিকেশ্যনত মানে বাধা জন্মায়। ৰেডিঅ' অন কৰিলে শব্দটো যে পোৱা জানা নহয়, কিহৰ পৰা আহে, that was his goal. So he was unable to find it initially, মানে it was not easy যে কৰ পৰা নো আহিছে, সদায় কিবা নহয় কিবা অলপ নহয় অলপ কিবা নহয় কিবা বেলেগ বেলেগ তাৰ সিগনেচাৰ তেওঁ দেখা পাইছিল। But because of his persistent, যে মই উলিয়াবই লাগিব, এই যিটো দৃঢ় যিটো সংকল্প যে মই জানিবই লাগিব। So he finally found out that there was a 4-minute delay every day. It came from a region in this space which was 4 minutes delayed. And then talking to other astronomers, other physicists, actually, he came to know that this is correlated to the motion of our galaxy, of our solar system within the galaxy. So essentially, every 4 minutes, we come to the same spot in the galaxy every 4 minutes later per day. So he was able to associate this emission, is a static SSR শব্দটো তেওঁ পাইছিল, he was able to associate it to the center of our galaxy. So this was the first confirmation of our galaxy center being a radio emitter. So it kihor pora radio hai, we'll come to that later, but his persistence, so it was a chance discovery, and that led to a birth of a new field in radio astronomy, called radio astronomy. He is this Growth Traber, অন্য এজন ব্যক্তি, who's regarded as the pioneer, one of the pioneers of radio astronomy. So he was an engineer by profession. 21 বছৰ বয়সত he was so কি বুলি ক'ব আৰু, মানে hands on, তেওঁৰ ঘৰৰ পিছফালে নিজে হাতেৰে স্ক্ৰেপ মেটেল ব্যৱহাৰ কৰি কাঠেৰে হেৰি বনাই, তোমাৰ ষ্টেণ্ড বনাই, টেলিস্কোপ বনাই, জেন্সকিয়ে যিটো সিগনেল ধৰা পেলাইছিল, সেই সিগনেলটো তেওঁ নিজে বনোৱা টেলিস্কোপেৰে তেওঁ he wanted to study the galaxy. And the map, the radio map, his is one of the first radio maps that went a long way into into the development of this field. So these are two remarkable people whose persistence, whose excitement, whose attitude led to the emergence of a whole new field that we today know as radio astronomy. I could not mention Jocelyn Bell Bonner's discovery of pulsar. Again, the by this time 1967 তেওঁ pulsar discover কৰে. I hope you know what pulsars are. So these are compact objects, small neutron stars that now we know that they keep rotating, and every time every time lighthouse দেখিছে নহয় বা জানা নহয়, lighthouse. So what does a lighthouse do? তোমাৰ যে লাইটটো যদি তোমাৰ এনেকে চাৰিওফালে ঘূৰি থাকে, whenever the light faces you, তুমি এটা ফ্ল্যাশ দেখা পোৱা নহয় জানো? The moment the light comes to your line of sight, তোমাৰ line of sight লৈকে যেতিয়া লাইটটো আহে, you will see a flash, right? And then it disappears. So this is like a pulsar, on off on off. যেতিয়া লাইটটো তোমাৰ ফালে আহে, on হ'ব, you see something, and when the light goes away, you see darkness. So rotating neutron stars, they emit radio waves towards, when they emit radio waves towards us, we see them as pulsars. So what Jocelyn Bell Bonner saw, so they recorded this signal in a chart recorder, and was very very curious at that time. Iman regular interval or key signal ahise no, people did not know what pulsars were back then. So she doggedly, patiently persevered and collected charts from days, maybe weeks, and found out that there was a periodicity to, and she was able to eventually associated with a astronomical object, which later came to be known as, or came to be associated with neutron stars. Or theoretical physicists বলে বিচাৰি আছিল যে there should be neutron stars, there should be neutron stars, and this was the first discovery of it that led to many remarkable physics later on. I'll not get into the details of those, but this is one of my favorite discoveries in the field of physics, and radio astronomy played a key role in it. এইটোতো তোমালোক সকলোৱে চাগে শুনিছাই, পেপাৰে পত্ৰই চবতে আমাৰ আমাৰ হাতীপতিৰ, আমাৰ মিল্কি ৱেৰ চেণ্টাৰ অফ মিল্কি ৱে যিটো ব্লেক হোল আছে, সেই ব্লেক হোলৰ ইমেজ, ৰাইট? So this was in May 2022. What I wanted to highlight about this image, I mean, it's a remarkable discovery. It's a remarkable discovery, but what I wanted to highlight was the fact that this discovery was made possible by collaboration amongst many international researchers, not just one country, many international researchers with telescopes, radio telescopes scattered all across the globe. So it's a massive collaborative effort, the result of which was this beautiful discovery of a direct evidence of a black hole using measurements, direct measurements. So it is remarkable. So collaboration is something that I really look forward to with people. Okay, so why multi-wavelength? Multi-wavelength kyo? Multi-wavelength মানে কি? আমি বেলেগ বেলেগ বিভিন্ন wavelengthত I'm assuming that all of you are familiar with physics, basic physics সবে কৰি আহিছা. Is that correct?
Yes, Wasim da, these are
okay.
all basically physics students da.
Okay, perfect. So if I say wavelength, I can forgive myself, right? I mean, I don't have to be apologetic. Okay, all of you know what wavelengths are. So the electromagnetic spectra, it's a broad band, right? It starts from on one end, it starts from very high energetic ultraviolet rays, or what do you say? আটাইতকৈ কোনবা কবনে, what's the highest energetic, the smallest wavelength radiation electromagnetic spectrum or?
Participants, please respond. Participants, please respond.
ঠিক আছে বাৰু, মই কৈ দিম gamma rays. So gamma rays are the most energetic I mean, it's on the extreme end, the low frequency end of the electromagnetic spectrum, whereas radio is at the it's the lowest energy electromagnetic end of the electromagnetic spectrum with the longest wavelength. What we see, আমি যেটো দেখা পাও চকুৰে, that's a tiny fraction of the entire electromagnetic spectrum. মই electromagnetic spectrum টো ইয়াতে দেখুৱা নাই, but I think all of you know that the visible spectrum is just a tiny bit of the entire electromagnetic spectrum. So what you are seeing in this image here is our Milky Way, our galaxy, in optical. চকুৰে দেখা পোৱা যিখিনি wavelength region, সেই wavelength regime আমাৰ হাতীপতি, আমাৰ মিল্কি ৱেটো এনেকুৱা দেখি. Most of it looks like dark, একো নাই, আন্ধাৰ, and only in the plane, galactic plane, you see some emission, strong bright emission. Of course you see stars everywhere, but that's all right. কিন্তু galaxyৰ পৰা আহা emission টো এনেকুৱা যেন দেখি. Most of it is confined to the galactic plane alone. If we look at radio, sorry, if we look at optical wavelength, চকুৰে দেখা পোৱা wavelength, normal দূৰবীনেৰে চালে বা normal telescopeৰে চালে এনেকুৱা দেখে. ৰাতি যদি ওপৰৰ ফালে চোৱা, লাইট পলিউশন যদি নাথাকে, চহৰৰ বাহিৰৰ পৰা যদি চোৱা, কোনোবা গাঁৱৰ পৰা যদি চোৱা, অলমোস্ট এনেকুৱা দেখা পাবা হাতীপতি. But if you look at different wavelengths, so this image is the same as this one, optical. But if you look at different wavelengths, you see an entirely different picture. So the gamma ray swa, it's more or less like optical. Optical jenokwa dekhi, gamma ray to more or less tenokwai dekhi. X-ray okonman beleg dekhi, you see much more in X-ray. Optical to the kolue. Infrared ako opan beleg dekhi. Infrared you can see some other features. And radio totally beleg dekhi, completely beleg dekhi. There are of course correlation between radio or X-ray to the swa. There would be some correlation, but what I'm trying to say is different wavelength or বিভিন্ন wavelength তুমি যদি সোয়া বা sense করা, if you study the galaxy at different wavelengths, you see a completely different picture, and that has something to do with the basic physics. The radio core পৰা উৎপন্ন হয়, ইনফ্রারেড কোর পৰা উৎপন্ন হয়, অপটিক্যাল কোর পৰা উৎপন্ন হয়, এক্স-রে কোর পৰা উৎপন্ন হয়। So it gives you clue by observing at different wavelengths. It gives you a clue of about the different physical properties of the object that you are trying to study. So it allows you to make a more complete maybe a theoretical analysis, maybe a model, a more complete model, a more complete understanding of the object that you are studying. A kind of multi-wavelength is essential. So that's the justification for using multi-wavelengths, and I am picking up today radio bits of it, in which my expertise lies. So এখন চার্টত I'm just trying to tell you যে কি কি বিভিন্ন wavelength key astrophysical objects you can study and what are the physical properties. For example, X-rays, they're good to study gas clusters by galaxies, supernova remnants. You will put anyway. So বিভিন্ন wavelength you can study different physical properties, and yeah, you can complete your understanding of the objects that you want to study. All right. So a brief I mean, it I don't think I need to spend much time here. I just picked up a slide from my friend Dr. Jennifer West. She was very kind enough to provide me some of her slides from similar talks she presented. So these are three of the world's largest telescopes currently operational, single dish telescopes operating at radio frequencies. So one that you see above is a 100-meter dish at Effelsberg in Germany. Then there is this 76-meter telescope. This is a huge telescope. 76-meter telescope is a very large telescope. At Jodelbank, you can see this Park 64-meter dish at close to where I am in Australia. It's in a place called Parks. And all of these telescopes are steerable. Mane, you can move them. These are large telescopes, but fully steerable. You can point it to any part of the sky that you want to. But why do you need a big telescope? So I think most of you are aware of resolution and collecting area. So the bigger the telescope, the more is the collecting area, which means the light gathering power of the telescope is more. তার মানে, with a larger telescope, you'll be able to see fainter objects. So if you want to make your telescope sensitive to faint emission, faint objects, you need bigger telescope. So that's one of the reason to go for a bigger telescope. The other reason is resolution. If you want to separate two stars, say very close by, or if you want to resolve out features within a galaxy, right? You need a bigger telescope. So the resolution goes inversely as the size of the telescope. That means jiman fine resolution bisara, himan dangor telescope tumar darkar. So that's the motivation of going for larger telescopes. But building big telescopes is a massive challenge. It's a huge engineering challenge because it's not you can't it's not stable. Steer To be able to steer a massive telescope, we do not yet have the resources or the engineering abilities to do that. Plus, the costs will go high. Is it making sense? So this was the Green Bank telescope. I forget in which year it was. This is a 100 meter telescope, and then this is what happened. In 1988. So fortunately, this is in the USA in a place called Green Bank. This telescope has been revived, and today structural engineering, whatnot, it's one of the best single dish telescopes that there is. So yeah, it's not easy to construct these telescopes. They're massive. They're really massive, and their mechanical stability is a challenge, as an engineering challenge. So human beings, as you all know, are smart people. I mean, we are smart beings. We never give up. So okay, Amibaru, we cannot design steerable telescopes. So what about telescopes that doesn't need steering, like fixed directional telescopes. You can't steer it, but you can still see the sky as the sky moves past, right? And then add some electronic trickery to do some phasing, to cover not just the sky right on top. You can do some phasing to also steer it electronically a little bit. So these are constrained. You can't fully steer them. But the key design aspect is then they are anchored to the ground. So on my right, you see this Arecibo 300-meter telescope. This used to be the largest single-dish telescope, non-steerable, but largest single-dish telescope that was constructed in I think what was regarded to be a crater hole. The local profile of the Earth here was like a parabola. So they made use of that local depression on Earth to construct a parabolic or spherical dish here that served as a 300 meter. 300 meter is big, huge. The collecting area is like 0.07 kilometers square. Anyway, so this is in Arecibo in Puerto Rico. আর এতিয়া বর্তমান the largest single dish telescope is in China. It's a 500-meter aperture spherical radio telescope, fast. Uh, it's an engineering marvel. I mean, all of these elements to keep them part of the same spheroid. It requires huge stability. It requires precise design, and it also requires adaptive optics. So it's an engineering marvel in almost all design aspects. And you can see the improvement in the collecting area. So it's already 0.2 kilometers square compared to the last largest single dish telescope. And the resolution is 40 arc seconds, 40 seconds of an arc compared to Arecibo. It's almost double. The resolution is twice as good. So, but these are fixed telescope. You can't mechanically steer them. So, but again, we need larger collecting area, and we're never satisfied. So, what do? There are techniques. I think Bornali must have touched upon how to synthesize large aperture. So yes, we cannot make one big dish that's steerable, but we could cleverly connect several small dishes together so that combined together they can be used to synthesize a large aperture. So this is a picture of the VLA, the Very Large Array in the United States, in New Mexico in the United States. So the maximum distance is, I think, 25 30 kilometers, maybe 27 kilometers. Don't take my word for granted. I should have known this, but I don't. But it's somewhere between 25 and 30 kilometers, the maximum baseline. And it's an array comprising of 30 dishes. So it's an interferometer. You combine now, each pair of antennas can be combined together. Yeah, the signal from each individual dish is combined together appropriately, and the net result would be a telescope which is as big as this. For example, in this case, I think it would be a radius of 30 kilometers if the diameter of VLA is 30. So you can easily construct with current technology, you can easily construct or synthesize an aperture as large as 200 kilometers with this technique. So basically, a collection of multiple small telescopes synthesizing an aperture of 200 kilometers. But you can never make a 200-kilometer single dish telescope. That's just impossible. Okay, so this is just a picture. If this is actually a part of the galaxy. I think this is the Small Magellanic Cloud. In reality, this looks like this. You can see the fine structure, like the hair-like structures. If you used only a single dish telescope, you'd see this. It still traces out মোটামুটি এনেকুৱাই দেখি, right? But it loses out the fine scale structure. এই যে hair-like structure বোৰ ইয়াতে আছে, ইয়াতে যে দেখিছা, a single dish telescope doesn't have the resolution to separate them out. The problem with interferometer is, although you can synthesize a large aperture, it's not actually one contiguous aperture. It's like bits and pieces of a large aperture. মানে a 200 kilometer, sorry, a 30 kilometer radius. It's not fully filled with these dishes, right? There are gaps, and gaps create problems. Think of a mirror with holes in them, right? You can still see yourself, but there will be distortions. Because of those distortions, you do not measure certain parts of the true image, so you end up again, you end up seeing the fine scale structures, but you miss the large scale component of it. Right, the single dish images are good for picking up the large scale structure, whereas interferometers are good at picking up the fine scale structures. And if you combine the two, there are techniques you can combine the two to get the true picture. Anyway, both have their plus and minuses. So hitule mo najaও, আজিৰ ডিসকাশনত নাযাওঁ. Someday, if I come there someday, I'll discuss more about what interferometers do, what single dishes do. Anyway, so very briefly, when did radio astronomy start in India, right? I already 1933 আৰম্ভ হোৱা বুলি ক'লো, in the US, Carl Jansky আৰম্ভ কৰিলে. So it was not too long. So in India, we had our first radio interferometer in a place called Kalyan near Mumbai in 1965. So Govind Swarup, unfortunately, he's no more with us. He is regarded as the pioneer of radio astronomy in India. I'd also like to consider Radhakrishnan, Professor V. Radhakrishnan from the Raman Research Institute, who was equally motivational in promoting radio astronomy research in India. So this is the first radio telescope in India, built in 1965. This is I think immediately after that, again, the genius of Swarup, Professor Swarup, he identified a hill in Uti, in South India, a state in Tamil Nadu. Sorry, a town in Tamil Nadu, state of Tamil Nadu. So the uniqueness about this telescope, I don't know how many of you know. So have you guys heard about different kinds of telescope mounts? Equatorial mounts, Dobsonian mounts. So an equatorial mount is something that's aligned, that's inclined, whose base is, or how should I say it, whose optic axis is inclined at an angle which is equal to the latitude of the place. So this particular place, Uti, and the inclination of the hill matched very closely to the latitude of Uti, which means if you constructed a radio telescope on parallel to the hill, with the base parallel to the hill, it would serve as an equatorial mount. This means that you can track the same parts of the sky. What does an equatorial mount do? You can track the same part of the sky without having to have two with just one degree of rotation, degree of freedom. You can track a given part of the sky. Alt-azimuth mounted, you will always have to have 2 degrees of rotation in order to track a given part of the sky. That's the beauty of equatorial mount, and this was a marvelous design, in the sense it made use of the terrain itself to convert this telescope into an equator, or to make this telescope work as an equatorially mounted telescope. Anyway, again, each telescope, there is lots of history. We'll just move forward. So this, I think most of you know. This is the giant meter wave radio telescope. A part of it, here you see only 5 dishes of the 45-meter dishes. This is in Pune, well, close to Pune, in a place called Narayangaon. So this is the largest array operating at these frequencies. So GMRT operates close to from 200 megahertz to about 1.6 gigahertz. So at these frequencies, this is the largest array that exists. Again, a vision of Professor Swarup and lots of work from the radio astronomy community in India. This is maintained by the National Center for Radio Astrophysics, and is one of the best telescopes that there is in the world at these frequencies. So, coming to new generation radio telescopes, the first image I show you here is that of the low frequency array. It's called LOFAR, popularly known as LOFAR. Again, it's a the thing that I like about this is the collaboration between various countries. So primarily the telescope elements are located in Netherlands, but there are longer baselines that's located in 7 other European countries. So it allows you to increase the resolution by having longer elements, by having baselines separated or elements separated by a longer distance. You can have a higher resolution. So yeah, so this is one of the images I decided to pick up. One of the beautiful images that LOFAR produced. Again, look at the this is the same part of the sky invisible in the light that we see with our eyes. This part of the sky looks like this. Whereas if you look at low frequency, that LOFAR operates in 100 something megahertz, 150 megahertz, you find out all these structures that you cannot see in optical. So it tells you much more about the same object, what it is, what the physical processes going on, what the physical properties of this region. So the power of multi wavelength astronomy. In this particular case, this is a very low frequency observation of, I think this is the Virgo A. Yeah, it's one of the brightest sources in the northern hemisphere. So this is the Meerkat, which is a telescope of 64 individual fully steerable dishes located in South Africa. This is a prototype or precursor to the square kilometer array. I was talking to you about the SKA, square kilometer array, because অলপমান কৈছিলো. This is the future generation telescope. So this telescope is one of the precursor. মানে ডাঙৰ project এটা বনোৱাৰ আগতে you need pilots, right? To test the technology, to challenge, to identify the challenges. Kino challenges ahibo dangor telescope to বনোৱাৰ আগত. So this is one of the. It's a very big telescope. It's a very big project, but still tiny compared to SK. So it's a precursor to the SK. So some of the results, a spectacular image that this telescope generated of this region towards the center of our Milky Way. It's a beautiful image. It's lots of supernova remnants never seen before, lots of H2 regions. What are the streaks? They were key, still not very clear, but this telescope brought it out in this detail. It was observed before, but not with this degree of detail. It's amazing. It's beautiful. Ever key. What are these? So it opens up a whole new possibility. These telescopes, new generation telescopes, into rewriting the story about the same objects that people had studied in the past. So more and more information are coming out. So the physics will be understood even more with these new observations. This is one of my favorite images from Meerkat. This is MWA, yet another precursor to the SKA. This is a telescope that sits on the Western Australian desert. Yeah, I think I'll not get into the detail of this, but just imagine the size of these telescopes. There are 4,096 spider-like, and I mean 4,096 elements. So each 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3. So 16 in one element. So okay. So this a single block is called a tile. Each tile is comprised of 16 elements, and there are 4,096 of them. This is not the entire area. This is just a picture of a small region of it. So overall, there are 4,096 elements. Imagine in a desert. Well, I'll come back to why we have to go to the desert a little later. But imagine in the desert having to maintain power, having to maintain connectivity. আৰু কিবা যদি বেয়া হয় তাক ঠিক কৰিবলৈ যোৱা, right? So imagine the challenges. of keeping 4096 elements working functional ঘৰত কেই মাহত আমাৰ টিভি বেয়া হয় কেই মাহত আমাৰ ইলেক্ট্ৰনিক গেজেটস বেয়া হয় right so so you have to be very careful in designing this so on and so forth so this is uh it's not as if this is an okay this is an image processed image so this image that you see here is indeed observed by this telescope but the orientation is not the same it's just a collage of how of the telescope and what it was measuring again the picture of the galaxy this is the galactic plane but observed at the frequencies of MWA which is like 200-ish megahertz. So great detail because of long baselines. These telescopes are spread across quite some distance, so you get very fine details even at these low frequencies. All right. I thought I will delve a little bit into more details about ASCAP, the Australian Square Kilometre Array Pathfinder. This is also a precursor to the Square Kilometre Array. So this is something that I have been working on for the past 7.5 years. I'm very familiar with it, and so maybe I'll be able to give you a more complete picture of the challenges involved. I mean, each telescope will have their own challenges, but yeah, at a higher level, I think the challenges are similar. The details can be spared at this moment. So, what is ASCAP? So, it's an interferometric array of 36 fully steerable dishes. These are 12-meter dishes. These are not very big dishes. Tiny, well, not very tiny as well, but 12-meter dishes, and 36 of them, and spread around a distance of about 6 kilometers. So 6 kilometers is the longest baseline that you can have with ASCAP. The operating frequency is 700 to 1800 megahertz. At any given instant, however, you cannot observe at all of these frequencies. At any given instant, you can observe 288 megahertz with spectral resolution of 15,000 channels. So basically 288 megahertz divided by 15,000 channels, it's like 18 kilohertz resolution. You can study the sky in one go. So I'll tell you something about, without going into the detail again, something about what's unique about this telescope. Remember this phased array feeds. It's a new technology. It's a novel technology. And often you'll hear if you hear listen talks about ASCAP, often you'll hear about PAFs. So PAFs are nothing but phased array feeds, PAF. So they're shortened to call PAFs. And then the other novelty in this telescope is the third axis. So usually telescopes have 2 degrees of freedom, one along the azimuth and the other along the altitude, right? But ASCAP also has this rotation degree of freedom. I'll come to it in a little while. So basically, this telescope dish can also rotate, can also spin. It can spin. It can move about this axis. It can move up and down, and it can also spin. So that is crucial for ASCAP phased array beams to produce high dynamic range images. I'll show you. The other unique thing about telescopes like ASCAP is the very high data volume and rate. So this is one of the major challenges in modern day big data radio astronomy. You have enormous rates of data and enormous volumes of data coming at enormous rates. So processing them becomes a big challenge. You cannot do this in a desktop. You cannot do this in the most powerful desktop. You require supercomputers to process the data coming out of these modern telescopes. So that's another key a skill that would be very useful to acquire in order to get into big data, not just astronomy, big data science. Astronomy is perhaps the biggest data that we generate now. So where is ASCAP located? So this is the continent of Australia, and ASCAP is in the deserts, the Western Australian deserts here. So why do we have to have, why don't we have it near a city? Why do we have to go to an isolated place like a desert where it's so difficult to get power, so difficult to get, workmen, so difficult to get any infrastructure, right, for building telescopes? That's because the city is infested with things like mobile phone, television signals. It's completely, it's like much like you have light pollution. রাতে যদি তোমার শহরত যদি লাইট বোৰ জ্বলি থাকে, you can't see the sky, right? It's all polluted with light. The light from the terrestrial sources, আমার ঘরের light, আমার street light, right? Industry কারখানার light, they pollute the night sky, and you cannot see this the stars, the galaxies, so Korea. You have to go to the village where there is no electricity, or very remote areas. তেতিয়া তুমি দেখা পোৱা. Much like that, telephone signals, mobile signals, televisions, microwaves, these things interfere with our radio signals. So we want to go to a place where there is no connectivity at all, where there is no interference from man-made, human-made signals, radio signals. So that's why you need to go to remote sites. But that's becoming increasingly difficult. There are lots of satellites that transmit radio. That's another major problem. Even in a remote site, you cannot avoid aeroplanes. You cannot avoid satellites. You cannot avoid military radars. So even a remote site is not truly remote, but at least it's remote in the sense that the majority of the population are not interfering with your observations. So just to give you an idea, in an area of 100 kilometer by 100 kilometer, only 20 people live. So that is the population density of this area where you have this telescope. Just 20 people in a 100 kilometer by 100 kilometer area. Can you imagine this? So it's ASCAP is unique in the sense that it is a very wide instantaneous field of view. So here in this red dot, a typical telescope operating at the frequencies that ASCAP operates, this is the region that it will be able to see in a given instant. It is our field of view. So this is what we call field of view. But ASCAP, because of its paths, because of its phase array focal plane phase array feeds, the field of view is huge. Now imagine this galaxy Centaurus A. It's a beautiful galaxy. For it to be observed by a telescope like the ATCA is the Australian Telescope Compact Array. It's a telescope in very close to Sydney. It's in Narrabri. To observe this field, to observe this beautiful source with ATCA, you will have to have multiple pointings, thousands of pointings, hundreds of pointings. Whereas with ASCAP, you can just have 2 pointings and image the entire beautiful source. It's a big source, it's a huge source. So that's something that's new in terms of technology demonstrated by ASCAP. I was telling you about the third axis. So if you did not have the third dimension of rotation, if your telescope did not have this rotation degrees of freedom as you are tracking a source, what you will see is, so okay, this is blinking between normal observing and Rolex is disabled. So Rolex is disabled mane you're just tracking the source in the sky with an alt-as mount, right? You're not rotating your feeds, you're not rotating the dish. Heterocorrelate, you see lots of imaging artifacts, lots of errors in the image that you generate. Whereas if you rotate the third axis to compensate for the rotation of the sky is rotating, right? So if you compensate, what will happen if you also rotate along with to counteract the rotation of the sky? What will happen? The beam that your telescope is pointing to will remain fixed in the sky, by virtue of which you can get very high dynamic range images. I'll show you a video. So if you look at this time lapse, hang on, is it doing something? Oh, I'm surprised. Why is it not playing the video?
It's not.
Why is it not playing the video? Why is it not playing the video? Oh, this is not good. You'd have been able to see the effect of the third axis rotation. So I'll just give you a brief idea of what I'm showing here. So this is the focal plane array. Normally, right, any radiation falling on a parabolic dish gets bounced back to the focus, right? So a telescope usually has your dish antenna, your TV dish antenna has a receiver, right? which is at the focus of the dish. Just one receiver at the focus of the disk. So here, instead of one receiver at the focus, it has an array of receiver at the focal plane. What will happen? Ki hobo tetya? There is not just the radiation that's coming directly from the direction of pointing, right? So that will get captured. Wherever you're pointing directly, that radiation will get focused here. But say the radiation coming from this direction will get focused somewhere here, which means with multiple elements in the multiple detectors in the focal plane, simultaneously you are able to record signals coming from different directions in the sky. With one pixel, with only one detector, you would have only been sensitive to radiation coming from just that direction in the sky. So having multiple detectors, just imagine if you had a parabola and ask where will the ray bounce back to if it doesn't come perpendicular to the aperture. If it came at an incline angle, if it came at an inclination angle, it will not focus to the focal point. It will focus the ray to a point in the focal plane but away from the focus. So that's why you have detectors that are arranged in as an array in the focal plane. So this is the focal plane of the dish, 12-meter dish. And now by doing this, you are sensitive to radiation coming not just from the direction at which you're pointing, but also from direction that is slightly away. So this is the primary fundamental basis of being able to generate wide field of view. I'm sorry this video is not playing, so I don't know why it is not playing. I'll try one last time to see. Um, mm, 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 mm.
If you disable the pointer for a second and operated the
Let,
cursor, maybe it
let me
might
see.
help.
Can you disable করব?
Right click on the slide, I think.
কৰিলো একো নহয়।
No,
Laser
you're using
pointer click কৰো নেকি? তেতিয়া যাব।
PowerPoint.
Yeah. Okay.
Yes,
Thank you.
now it will.
Okay, good. I'm sorry. So just watch what happens. The time into time elapse video hoy. The time is passing. You can see the sky rotating, and nothing is being done by the telescope at this moment. You rotate corona, so you can see that the sky's orientation is changing. Sky's orientation to change hoy, then you will have distortions, right? You want to have a long exposure. Long exposure on a changing field will make the image fuzzy, right? This is exactly what is happening. The sky is rotating and you are not compensating for the rotation. But wait a moment. Now you will see, look at this. Here, do you see this? Here, the sky is fixed because you are also rotating the telescope by the same amount. So, are you getting it? The sky is now not changing because you are compensating the sky rotation by the third axis rotation of the telescope. So that way you can keep the field of view of your telescope constant, fixed, change no. So this is equivalent of saying if you stand in front of your camera and put in a long exposure, 2 second exposure deep light, if the subject moves, it'll be hazy, right? But if the subject moves and you also move the camera along with it, right? Then you'll be able to get a very sharp, undistorted, long exposure. Does that make sense? কোনো একো মাথা নাই মোক আকৌ দেখাও পোৱা নাই I can't see anybody.
Participants actually please feel to just unmute and speak up. Don't feel shy. There's nothing to feel shy about it.
I'll show you this once more. So here in this particular shot, the sky is moving. The telescope's third axis, the rotation axis, that is fixed. We are not making use of it. It's like a normal telescope. What happens is you will see that the sky will change, right? If you took a long exposure, what will happen is there will be distortions. So just notice this telescope is fixed with respect to the horizon, and the sky is moving. See. So this will lead to distortions. Jodi ami rotate nokoro, it will lead to distortions. Do you see that? The sky is moving and you are not rotating the dish. So yeah, like it. And what we want to do is we want to take a long exposure. So it'll become hazy, it'll become fuzzy. Dunia distortion ahibo. But same here. The sky is rotating, it's changing. Now wait. Now wait. Even this one here, notice. Notice that the sky is moving because it to Earth on this. Oh, I have to bring out the pointer now. This portion is the Earth. It on our horizon. And we are looking at the galaxy here. Notice that the telescope's frame is fixed to the galaxy or fixed to the sky. The Earth is moving. তার মানে আমি rotate করে, we are rotating the telescope in a way to counteract the rotation of the sky. And then what happens? See, see what happens now. The galaxy with respect to the detector will remain the same, and the Earth is moving. Do you see that? The Earth is moving, but the sky remains fixed with respect to the focal plane. So that is what the third axis is doing, which is critical to get high dynamic range images. Anyway, I'll skip this. I'll skip this. If you're, since you guys are from physics, I can very briefly dwell on this. So this is the focal plane, right? I'm just drawing a schematic of the detectors, but essentially these detectors are in the focal plane. So now, if you're pointing at the source, the diffraction pattern of a source, of a point source in the far field, right, of your telescope is an airy pattern, right? The focal plane distribution of electric field looks something like this, right? The airy pattern. For those of you who have not got into this yet, you will get into this either in the second year or in the third year. All I'm saying is a source in the far field, when observed by a circular aperture, will create a diffraction pattern which is called the airy pattern, and it looks like this. High intensity at the center, and then there will be low intensity, and then there will be high intensity, low intensity, and so on and so forth. It will be a ring-like structure called the airy pattern. Now, to form beams, escape is a beam board je bonai, multiple beams je bonai. Actually, we do not have we have about 188 elements, individual elements, 1 2 3 4, and 188 elements ase, but we cannot form 188 beams in the sky. We cannot have 188 detectors looking at 188 different directions in the sky, simply because of compute bottlenecks. Our iman compute power of one eye that we will be able to do this for 188 independent pointings. So what we do is we combine several of them together and to form one phased beam, and overall using all the 188 elements we form about 36 beams. So basically we form beams looking at 36 different parts of the sky, making use of combinations of these 188 individual detectors. So this beam corresponds to, or this response corresponds to, an emission coming from the pointing direction. So beam forming kenege kore? So we look at a calibrator source which we know to be a point source which is strong, and we know that its response on these detectors should be an airy pattern. So now we measure individual signal measured by individual detectors and ask, are we getting the airy pattern or are we getting some distortion from the theoretical airy pattern? Jodi sob thike asil, if everything is all right, if the instrument is behaving all right, then a point source at infinity illuminating my circular aperture of the dish should produce an airy pattern. More central element bore should have gotten very high intensity, and as I go away, my intensity should have dropped in a theoretical fashion. If it does not, then I know by how much it does not, and then I can correct it. And that is what we use to electronically form beams, right? Anyway, again, sometime later. So by electronically forming beams, so this, for example, was a beam that is formed on the direction in which the telescope is pointing. I can combine several elements in this region. Oh, you're not seeing the pointer now, sorry. So this is the beam that's formed at the pointing direction of the telescope. I can form another beam combining elements, phasing elements here in this part of the path, uh, to form a beam in a different part of the sky, right? So এনেকে মই 36টা beam একেবাৰতে instantly I can produce 36 beams, allowing me to look at 36 different parts of the sky at the same time. So which means that now my telescope is not just one telescope of 36 antennas. It's like a 36 array of telescope with each with 36 antennas. বুজি পাইছা কি কৈছো? If I had only one beam, মানে এটা one direction that I was sensitive to, that I was able to look at, then it would be an array of 36 antennas with one direction, right? But now simultaneously I'm looking at 36 directions, which means this is a telescope 36 times more bigger, 36 times more data. It's a huge amount of data that we are trying to record and measure. Anyway, I'll not go into this detail. This is something funny. Uh, uh, do you know what happened? You see this to be burnt, right? It কেনেকে হৈছে জানা? The surface of the dish was covered with dew, মানে নিয়ৰ. So ৰাতি নিয়ৰ পৰি বা বৰষুণ পৰিছিল নেকি, বৰষুণ পৰি পানী যিখিনি জমা হৈছিল তাত সূৰ্যৰ পোহৰ পৰি it got reflected into, it got focused into this position and it burnt it. So we have to be very careful about this kind of things. This was not taken into account in the design phase. So it was very rare. It's very rare that it happens, but yeah, it just so happened that yeah, this instrument got damaged. It had to be replaced. So anyway, this is one of the practical challenges. Primarily because we beamform on the sun. The sun is a bright object, and if there is water accumulated on your surface and the sun is shining on it, this is bound to happen. So yeah, just a few numbers before we go into question answers. Apurva, more kiman time ase?
Yeah, Wasinda, we have 5 more minutes.
Okay, I'm almost at the end.
Fine.
So this is the kind of data that we are talking about. For ASCAP, for example, 21 terabits of data per second is what this correlator needs to correlate. So basically you need 340 teraflops. A machine, the compute power that is required to process this is like 340 teraflops. After the processing is done, you do some averaging, you do some integration. The output data rate that we astronomers get to deal with, to make images, is like 2.5 gigabytes per second, which means every 8 hours we generate about 72 terabytes of data. So we need to deal with this amount of data to make images. You cannot do this on desktops. This is just a brief layout. The telescopes are in the desert. The telescopes go through several processing within the observatory itself. They're correlated on site in a control room on site, which is in the desert, and then the 2.5 gigabyte per second link that I was talking about, the correlated data after some averaging integration, they're passed over very high speed fiber across several hundred kilometers from the desert to Perth, where the supercomputer exists. So it is on this supercomputer, it's called the POSI Research Center, POSI Supercomputing Facility, where we have our supercomputer, where we actually take this data and process them to make images. So it's a massive project, and SK is going to be, I don't know, n times more complex than this. So the data rate is one of the biggest challenges. How do you handle such big data rates? So you can do the math. 2.5 gigabyte per second mane kiman hobo, and the data is coming day in and day out, non-stop. This is our current supercomputer, a picture of the current supercomputer called Galaxy. It's a Cray supercomputer where we do our processing. Not important. So you need special purpose software. You cannot just use your Python or your other scripting language, right? Or C++, just normal C++. You need parallel programming. You need ways to make smart codes. You need ways to write codes that can make use of supercomputing facilities, so on and so forth. So you need special purpose software to deal with this data, these kinds of data. So computing is going to be a major skill set that will be valued for this kind of research projects, not just in astronomy. Same thing repeated over and over again. This just gives you an idea of how much data sets are produced every night. So total after processing, so before processing you get something like 100 terabytes per night. After processing, you also generate image products, you generate intermediate products, but it can grow up to 350 terabytes per night, per 12 hours of observation at ASCAP. So 300 terabytes per night. Just imagine what kind of storage space you would require. So often I get this kind of mail saying, "Dear Wasim, it is time once again to request a reduction in users of the disk." So I often get this. So delete data. You have too much data there. Delete it if you can. And then there is contention between collaborators, right? So I want to use the supercomputer, my other friends want to use the supercomputer, and often supercomputers have queues. It's like a traffic thing. So sometimes it can delay other people. If I have submitted lots of jobs, it can delay the jobs of other people. So yeah, there's fun things happening because we share the same supercomputer. But at the end, what I think is progress requires team effort. So this is the way we work. We have busy weeks organized every few months where we crash upon problems that we encounter collectively, and then we go into small groups, try to solve them, and come back, assemble again. And yeah, you can see some of this with some of the group effort leading into some fantastic images. Going from here to something like this. So it's a collective effort. This is one of the recent images from ASCAP. This is of a supernova remnant. It's a beautiful image. I didn't have the optical image, but you see nothing in the optical. And in radio, you see this bright, beautiful supernova remnant. And other galaxies as well. Lots of other galaxies. In radio, almost every dot that you see are radio galaxies. It's beautiful. Some more images from ASCAP. This is also of a supernova remnant SN1006. And so many fine structures, so many. Oh, by the way, look at the size of the moon. So just to give you a perspective of how big our images is, if this is the moon, this is one single image coming out of ASCAP. Lots of other galaxies, Some more challenges. You have to be careful about imaging with the right parameters. Otherwise, these things are artifacts of imaging. So you have to take care that your imaging software do not run wild. You should be using the right parameters so that you don't waste supercomputing time. So if you do not do the right thing, you see two sources. This is a fake source, so you might end up thinking that this is a true source. But if you do the right thing, if you do the right kind of correction, then this source goes away. So you have to be very careful. You have to keep an eye on these things. Otherwise, you will end up interpreting incorrectly your data. The other challenge is different science requires different tuning. So if automation is very difficult, and a human interaction with such huge data is also very difficult. So it's very difficult to handle this kind of complex emission. So if you ran it automatically, by automatically I mean a parameter set that you had optimized for a particular kind of observation. For this particular source, the center of the galaxy, you see all sorts of artifacts, all sorts of negative things. But if the human does get involved, if I look at the processing, I can fine tune my processing software in order to do the right thing. No negatives here. So it's a big challenge. It takes time. It takes patience, and to automate it is an even bigger challenge. And then lots of complexities because the number of elements that a telescope like ASCAP has, 188 PAF elements, right? 36 antennas, 188 elements, detect individual detectors. এটাও যদি তার বেয়া হয়, to find out which one goes wrong is a pain in the, it's a big pain for the entire team. So all of this that you see here are actually artifacts of some bad elements. Eta element kobat beya asel, and that's why it looks this horrible. The map of the galaxy does not look like this, as you will see. So most of the artifacts goes away. So in one case, in here, in this particular frame, you see this with the bad elements included, and in this you see this with the bad elements excluded. So some automated algorithm was used to identify the bad elements and exclude them from the processing, and immediately you get this beautiful result. Still not perfect because there may have been some more bad elements remaining, but you can see the point, right? So you have to rely on huge smart algorithms to identify bad elements. Yep. So yeah, I think I have exceeded the time. I did not intend to go on this long. I'm sorry. But yeah, what is next? With all the experiences that we have with ASCAP, with LOFAR, with Meerkat, with MWA, we are now on the verge of constructing this huge project that mankind has ever seen, the SKA, the Square Kilometer Array. So it's the next frontier, undoubtedly. It's a 2 billion euro project, which is a massive amount of money involving several countries, including India. So it's a nice time to get involved into astronomy. Astronomy, if you're interested, it's the perfect time to get into astronomy. So keep an eye on what skill sets would be useful for you. Computing for sure. Talk to other people, not just physics. Physics or holably is physics কথা পাতিব লাগিব. No, projects like this require interaction with computer science people, requires interaction with electronics engineers, requires interaction with electrical engineers, mechanical engineers, every domain that you can think of. Image processing, signal processing, digital signal processing people, or physics to lagi boy. So keep an eye, keep yourself open to talking to people, not just people in your department, but across departments. That is the key these days. Some of the key science drivers তোমালোকে জানিবাই, তো পাবাই ওয়েবসাইটত চালে আজকে কি কৰিব বিচাৰিছে, general relativity tests, right? Epoch of reionization. What was the universe like when it started, when things started to form, when early universe কেনেকুৱা দেখিবলৈ, cosmic dawn? How did the galaxies evolve? And any discovery, exploration of the unknown, magnetism, local universal magnetism কেনেকুৱা? So all of these things, this new telescope SKA is aiming to show us. And the great thing about it will be it'll be a huge telescope. It'll have a very big collecting area, so it'll be very sensitive to even the faintest of objects, and it will have very fine resolution. So মই এটা ভিডিও দেখুৱাই এন্ড কৰিম, মানে মোৰ টক এন্ড I'd just like to show you a video if you don't mind. 2 minute video, is that okay?
No issues, Wasim. Please go on.
Just 3 minutes. I have to find out where share now. ইয়াতে দিছিল নেকি হেৰিটো লিংকটো? Okay, I have it. Maybe I can share it here. I should share. How do I share it? Share to easy as well.
You'll probably have to stop presenting
Stop
first
presenting
and
and then
start
and then
presenting
share.
one window again.
Do you see something?
Yes.
কোনটো screen দেখি যাবা?
At the YouTube one.
Hang on.
Full screen কৰিলে I think there's a
Hang on.
possibility to play কৰিলে হৈ যাব.
মই যিটো প্লে কৰিম সেইটো পাইছা নে নাই?
SK, the world's largest radio সেইটো ন?
Uh, did you hear that? এইটো ঠিকে আছিল নে?
I mean,
Uh,
the video was coming, but the audio wasn't clear. But Himanshu shared the link, Wasimda.
Okay, good,
So
very good.
yeah, we'll share it
Thank
in
you.
the
Thank you
WhatsApp
very
group.
much.
huh.
So yes, I have come to the end of what I wanted to speak with you.
Yeah, I think it's time for questions now. So participants, please feel free to ask in whichever language you are comfortable. Please feel free to do that.
একেলগে কোনোবা কোনোবা আছে নেকি এটা ৰুমতে একেলগে? নাই না কোনো? আছেতো না নাই একেলগে কোনো নাই না সব সব পৃথকে পৃথকে আছে everyone is separated no one in the same room একেলগে থাকিলে অলপমান দিব পাৰিলো হয় ন
Yeah. So anyway, মই চাগে opening to কৰি দিওঁ এটা কুৱেশ্যনৰ অসীমদা।
Yeah, Himanshu, please
So
please go on.
so আমি জানো যে ইলেক্ট্ৰমেগনেটিক স্পেক্ট্ৰামৰ গোটেইখিনি ফ্ৰিকুৱেঞ্চি আমাৰ এষ্ট্ৰনমাৰ্ছৰ কাৰণে খুলি নিদিয়ে। Some part is reserved for military or maybe some commercial applications, right? So when we move to the desert বা তেনেকুৱা বেলেগ isolated জেগা তেতিয়া কি আমি বেছি স্পেক্ট্ৰাম এটা পাওঁ নেকি নে that is regulated worldwide যে ইমানখিনিহে আমি এষ্ট্ৰনমাৰ্ছক দিম বাকিখিনি will reserve for military applications or commercial applications?
তেনেকুৱা নহয় মানে when you say reserved astronomers are কাৰণে very narrow bands are reserved right আৰু
Exactly.
and okay and we are passive observers right we don't transmit we are not allowed to transmit we are only passive receivers so emit নকৰো but the problem is spectrum is also like it's precious right communication not lage of course military purpose lage tumar ADSB or that aircraft lage right so but the question is quote ataitkai where would it be the least interfering right wherever there is no human activity হেতুৱে মই কৈছিলো যে it's getting very difficult these days more and more difficult these days to come up with a region where there is no interference at all. Tomorrow question to কি আছিল? You cannot ask for reservation. I don't think that will work. It's just not economically viable. Nobody would reserve spectrum for radio astronomers.
No,
Nobody.
actually more question to asile something like that যে আমাৰ যেটো regulatory body, who is the regulatory body?
There is a lot of ambiguity in that as well. So there are regulatory bodies, but I think there is some it's not it's also a cross national issue, right? I mean, India, there would be someone who's regulating it, right? We have the information broadcasting ministry, we have spectrum regulating agencies in India, but there are international agencies as well. But I do not think that there is a unique organization that dictates everything for everyone. So what is regulated in some country may not be regulated in some other country, but growing I mean SK is one of the reasons where people are indeed trying to bring everyone affected under the same umbrella. It's still an ongoing process. I don't think there is one organization that does this, at least until now.
So maybe মানে অষ্ট্ৰেলিয়াত
CSIRO, we have a
এনেকুৱা
spectrum.
কথা আছে নেকি যে বেছি স্পেক্ট্ৰাম আমি পাম মানে
Uh,
তেনেকুৱাতো,
so,
or maybe
so,
less in USA তেনেকুৱাতো কথা নাই চাগে।
so I think we'll have to find out solutions in technology. I mean, it'd be impossible, or it would be naive to think that we'll get a clean spectrum. Right? All devices generate interference. Any electrical devices generate interference. Plus, like I said, since it's so much, I mean, communication is so essential that radio astronomers will not be given priority when it comes to preserving spectrum for them. So we'll have to come up with technologies where, despite the presence of these huge interfering signals, we would be able to subtract them out from our data and yet be able to measure the background, measure the sky. So there are techniques, so far costly, but there would be techniques, and they'll be easier in the future with hardware improvements, with when we have higher analog to digital converters, high bitrate analog to digital converters, it will become easier. But currently, it's a challenge currently. But the bottom line is, at this moment, it is a challenging domain, spectrum management and negotiations, as the parties involved are huge, and yeah, and there is no one body regulating everything.
Yeah. Okay, so I
think we
see
have,
a raised hand in the chat box. So
Ranjan Kalita.
please. Yes, Ranjan, please go ahead.
Yes, Wasim, yeah, it's a really nice talk, and lots of new informations are there. So I
Thank
have questions regarding the aperture size of the telescopes. So somewhere you mentioned that the aperture size also tells the resolution. So I'm not getting that point properly. I know
Right.
that aperture size will directly tell you the gathering power, light gathering power, or information gathering power, so that
Right.
entire objects can be seen. But what about the resolution?
So I love to bring in the okay. I didn't want to jump into the formula first. So I love to bring in this uncertainty relationship between how should I say it? Hang on.
Yes, I understand that it will be indirectly related, but directly is it related?
Indirectly, it's inversely proportional. So higher the diameter, larger the diameter, higher will be the resolution. So the separation, the ability to separate, the ability to tell one source from another that are close by, right? That ability will be higher if your telescope is larger, if your aperture is larger. If I convey it to you the other way around, I'm sorry, but what I meant was, two very closely separate sources separated very closely, you will be able to tell one from the other if you have higher aperture, larger dish size. So lambda by d, the frequency of the wavelength of observation is one parameter here, and the size of the dish is another parameter here.
Okay.
Oh,
So
Wasim, if I may, probably you are still on the browser screen. So
oh, I'm
are you
sorry.
trying to present the PPT screen?
Let me
PPT
stop.
window?
Yeah. Okay, is it now in the? Is it okay? I've stopped
No.
the sharing. I didn't want to share anything at this moment.
Oh, fine. It's fine. It's totally fine now.
so Ranjanda, was it clear, or do you want to
Yeah,
ask?
I get it. Yeah,
I think I
I
had
didn't. I
there
got
may have
confused.
been, miscommunication. No. I meant larger the aperture, higher is the resolving power, finer is the resolution, and I may have said
Angular. Yeah, okay.
angular
From
resolution is finer.
angular magnifications. Yeah. Okay, thank you.
So
So
other participants, if you have, it may type the questions in the chat box as well if you want us to ask the questions.
or any career related question if you want to ask. Okay, Wasinda, let me go ahead and ask another question since
Uh-huh.
you mentioned something about HPC, right? So some universities are now offering HPC courses, right? Masters in HPC. For example, ICTP, there's an excellent course at ICTP. So what are the prospects of HPC graduates in the next 5 to 10 years, say?
Like I said, in today's world where you will necessarily have to deal with big data,
Mhm.
learning or acquiring skills on how to use HPCs, how to use cloud computing, how to use supercomputers, that would be really invaluable. Uh, yes, I think if you have the opportunity in your colleges to enroll yourself into some of these courses, please feel free to do so. That'll be really helpful. And not just in astronomy, it'll be inevitable. Healthcare,
Mhm.
right? Data collection, pattern recognition, image processing, anywhere you can think of, you will require, I mean, you'll benefit by having a knowledge in high
Mhm.
performance.
And like, what are the possibilities of shifting to the industry? For example, I have seen many astronomers who after PhD gets absorbed in Netflix or whatever.
So, like I
Those,
said,
yeah.
I mean, A, it depends totally on you, and B, this skill set would be crucial. So, learning about uh, uh, HPCs or HPC techniques, learning how to r- write parallel programs, for example,
Mhm.
uh, cloud computing, for example. These are things that will be relevant in the near future. So yes, that will also open up scopes for people with these skill sets to easily jump into relevant industries, not just into research, but into relevant industries.
Yeah, in this regard, I also can add something. So not only the astronomy, in optical microscopy also nowadays in medical sciences, super resolution optical microscopy has come out, and that is like not a single image. You have to take lots of images, and that also requires around 100 of GBs data to compute. So for
Right.
that also you need HPC.
Mhm.
So it's really essential part in future.
Good to know. Yeah.
Biology, right? In chemical synthesis, there are lots of avenues where protein synthesis, for example, there are lots of avenues where you will require where you need big data. One suggestion for people who has this bent of mind to tinker with instruments. Have you heard of Raspberry Pis? These are
Yeah.
these are
Hmm.
very low cost compute systems, very affordable. Maybe you could motivate some students if your college could buy a few of them and ask them to design projects with it. There,
Hmm.
there's a good user community. There's a good user community on the web. So getting involved with Raspberry Pi, with microcontrollers that can be programmed using Raspberry Pi, it'll be really, 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 really interesting. So,
Okay, so thank you, Ranjanda, for adding it. So Wasimda, we have questions in the chat box.
uh-huh.
So Liponjiti Thakuria, so he has asked, Sir, is it possible that radio antenna could be operated from space? If yes, why we are building it in Earth?
Radio telescopes can be operated in space, and there have been experiments where they tried to put radio antennas in space. But you see, maintaining something in space has huge overheads, right? Uh, you have to be you have to be precise, and B, you are limited by resources. C, you can't just have big telescopes, right? So there are lots of limitations, technological challenges, and very common I mean, practical limitations. So the other thing is, yes, there are benefits of going up in the sky. There are, but the logistics is not favorable to us. The other thing is radio wavelengths. They're long wavelengths, so not much distortion happens to radio waves due to the intervening medium, like the ionosphere, for example. There are effects, but we can correct them. Unlike in optical, right? You have the seeing effects if the atmosphere is not, if there's too much water vapor, if there's cloud, you have problems. The radio waves being long wavelengths, you can receive signals without much distortion. The only limit is the size of the telescope. It can't be bigger than the Earth. The EHT is almost about the size of the Earth, the diameter of the Earth. It can't be bigger than that. So if you want a telescope to be bigger than the size of the Earth, people have tried sending elements of the telescope to space. So part of the telescope, part of the elements remain on ground, and part goes in space. But maintaining them is not easy. So that's why maintainability, ease of operation demands that it be on Earth. Does that answer your question?
Yeah, I think it's
So,
clear.
probably, yes. So we have another question. So Himakshi Kaushik, do we have SK in India? Or maybe I'll reframe the question to like something like, is India part of the SK consortium?
Yes, India is part of the SKA consortium, and India is building SKA regional data center. So NCRA, National Center for Radio Astrophysics in Pune, would be, I think, the lead organization that will be initiating this on India's behalf. But yes, India is very much a part of the SKA consortium. I think Ankur has a question. Is tracking of celestial objects using radio telescope? Yes, in principle, it's the same. Absolutely. The only advantage in radio is you can track a celestial object to some extent without physically moving the telescope, just by electronic phasing of the elements. So imagine you have two receivers, right? If you want to point directly upwards, you have to ensure that the phase difference between these two is 0, right? In that case, you are pointing upwards. If you want to point to a certain direction at an inclination, all you have to do is introduce a delay between the signals that you detect from one antenna and the other antenna. Because why? If it's coming at an angle, the ray from that direction reaches one antenna before the ray reaches the other antenna, right? So if you delay this signal electronically, you can measure both of them, you can correlate both of them at the same time. What I mean is, as if you increase the path length of the antenna where the signal has arrived before, right? And you increase the path length by exactly the same amount, that is equal to the extra distance that the ray had to travel to reach the other antenna. So by introducing this delay, and then if you correlate it, you are actually phasing it up in a different direction. So that's the basis of electronic phasing. So
Okay.
just introduce a path length difference to compensate for the differential path traveled by the ray from a given direction. That's the basis of phasing.
There are two more questions, if you permit. Can
Oh,
we?
please.
Yeah.
Go.
So there is one question from Sambhabi Datta. So she has asked, what changes were made in the Green Bank telescope when it was constructed again?
Oh, I think they took structural engineering very seriously, and I think they got more funds.
Mhm.
So yes. So speaking with structural engineers was crucial for this rebuilding of the telescope.
Okay. So finally, the last question. Sir, will setting up a telescope in moon have any advantage, as moon doesn't have any atmosphere like Earth?
More than that, so yeah, that's a very good question. But setting up a telescope on the far side of the moon would be advantageous, and not because of the atmosphere, but because of the pollution that we create. Our mobile signals, our aeroplanes, our satellite system. Well, satellites will still probably interfere, but very few on the far side of the moon. So yes, there are talks of putting up telescopes on the far side of the moon, and that would be really radio quiet, truly radio quiet. So we won't have, yeah, the RFI problem there. But again, the logistic is building it on the far side of the moon. You have to be very precise, very accurate, and that will be challenging. People are thinking about it though, including India at a point of time with ISRO. They were thinking about sending some instrument on the far side of the moon. That's a very good question.
So in fact, I believe there are also plans to put up a gravitational wave detector on the moon, right?
Right. They want to increase their baseline. Yeah.
Yeah.
So that's one thing I did not mention, but good that you brought it up. So complementary observations of radio in radio also helps establish that the signal detected by gravitational wave detector are indeed correct, right? Because once the gravitational wave detects, there are events that happens after it, and they happen at different wavelengths. So radio is one of the, yeah. So
Yeah.
in fact, radio wavelengths, multiple observations from different radio observatories was used to verify that the gravitational wave detector detected something that was real, something that was astrophysical.
Right.
So one thing that I would like to emphasize is talk to people. Don't feel shy of asking questions. You may think that questions are stupid, but believe me, even people who are Nobel laureates at the age of 80 ask questions that I would think is stupid, but they do ask. The understanding is always at different levels. Don't feel shy. There is nothing wrong in not understanding something. If you want to understand something, give up your shyness, just ask. And talk, not just with people in your field, as much as possible. Diversify.
So, Wasimda, any final remark?
Uh, I would like to congratulate you guys. I mean, this is fantastic initiative on all your part that you have been able to collect 50 people, 60 people in talks like this, and you have been able to do this sustainably from November. So that's remarkable, and I really wish you all my very best. In fact, I would love to meet you when I visit Guwahati next time. Visit Assam
Sure,
next.
sure. Just let us know your timings. We'll be happy to host you there.
In fact, I'd love to come to your college and meet with your students when I'm there. It might
Sure.
happen in April. I have not yet finalized the dates, but I
Okay.
might be in April.
Okay, sure. Sure. I'll be in contact with you there.
Okay.
Yeah. I
Thank
think
you very much.
Himanshu. Yeah. Himanshu, it's time for like the vote of thanks, and then finally we'll wind up.
Yeah, sure. So just for the sake of formality. So anyway, first and foremost, I'd like to extend my vote of thanks to Dr. Wasim Raja, who we fondly call Wasimda in our little community of young physics and astronomy enthusiasts in Assam. So yeah, big thanks to Wasimda for the talk on radio astronomy and the interactive session thereafter. And I also thank my fellow organizers for making this talk series happen. And last but not the least, or probably most importantly, thanks to all the participants who have been attending the talks live, and also those who would be watching the uploaded talk later on YouTube. So without you, the talk series would not have been possible. So thank you so much. So that's it. I'll cut it short, but at the end, I'd like to tell you that we'll be starting 2 more series shortly. So stay tuned. We'll inform you in the WhatsApp group, and also we'll update it on the website. So thank you everyone. Thank you so much. So